Good morning. Let's continue our discussion about Zener diode analysis. So we perform load line analysis. Today we'll continue on with piecewise linear and then look at an application of the Zener diode as a voltage regulator. So load line analysis and then piecewise linear. I believe we stopped on this slide, right? Stop here. So piecewise linear is basically an analysis technique where you break up the system or the system analysis into multiple pieces, and each piece has a linear relationship. Okay, so in this case, piecewise linear simply means we are representing the diode forward and reverse characteristics with a voltage source and a linear resistor. Resistor, of course, has a linear relationship between voltage and current. And so the Zener diode, when it is on, is represented as a voltage source in series with the Zener resistance RZ. Okay, that's the Zener resistance RZ when it is on, when it is turned on. So the representation would look something like this. And that would be VZ, and it would be RZ. Now, obviously, RZ is a model, right? It's a model similar to the diode resistor, RD. It is part of the Zener diode. We cannot separate it out. It's not a physically separable component. So if we wish to analyze the same circuit as in the load line, which is this one right here, we would replace it with a series resistor RZ. RZ is part of the spec. So in the spec sheet from the manufacturer, you would have VZ, RZ, and right now you're talking about also PZ, power rating. It's part of the diode spec. Okay. So if you want to analyze this, we need to determine the diode forward current, diode current flowing through the Zener diode. Well, let's first assume that the diode is on. If the diode is off, that means it's just an open circuit, right? It's not conducting. So if the diode is on, then the voltage source should have the voltage of the Zener diode. Voltage of the Zener diode is 5 volts. VZ is 5 volts. So 5 volts Zener plus 100 ohm resistor in series. Since everything is in series, we can simply analyze by applying KVL around the loop. When you apply KVL, you obtain the expression 20 volts minus the voltage drop across 5 kilo ohms minus the voltage drop across RZ minus the Zener voltage should sum up to 0. Only one unknown in there, which is the Zener current IZ. Solve for IZ, you obtain a value of 2.94 milliamps. Our assumption was that the diode is on. If the diode is on, then current should be flowing through the Zener. Should have a positive number, meaning IZ should be greater than 0, which is what we obtain, 0.94 milliamps. So our assumption is valid. Okay, assumption is valid. If we compare this number with the load line analysis, let's see, right here. With the load line analysis, we determined it was 2.9 milliamps. The load line was a graphical technique, and so we'd have to zoom into the graph to get a very precise and accurate number. But we obtained 2.9, and with the piecewise linear model, we obtained 2.9. So still pretty close, not too far off. All right, let's take a pause. Let me know if you have any questions. The Zener diode, the load line right here, that was because, again, the slope is exaggerated right here. That's why. It was a completely flat line, I mean, completely vertical line with no slope, then we'd say it's 5 volts, right? But again, this is just, it's slightly exaggerated just to be able to find a value. Yes. Do you think is the piecewise linear model? Yes. More than the graphical, yes. Most calculated models would be more accurate than graphical ones. Yeah. Yeah. All right. Well, then let's look at the Zener application as a voltage regulator. This is by far the most important application. So before I begin explanation of the analysis, let's simply look at how the regulator would work. Okay. So we have a voltage source and a resistor in series. That's not part of the supply voltage, it's simply a current limiting series resistor. So sometimes that resistor R, this resistor R, is also referred to as the series resistor RS. Okay, RS. So we have a voltage source, current limiting series resistor of R. We have a load resistor RL on the far right. And we wish to regulate the voltage that is supplied to RL. So what is meant by regulation? In this case, when we talk about voltage regulation, like electrical voltage regulation, we are referring to keeping the voltage constant. We regulate the supply voltage, or we regulate the system so that the load resistor sees a constant voltage. Okay, that's what it means. So voltage regulation here refers to keeping the voltage constant. As an example, we plug our electronic devices into the wall outlets, we expect it to be 110 to 120 volts. We expect that to be constant, but there's always fluctuations in the voltage. During times of high demand, the voltage would drop a little bit. During, let's say, thunderstorms, lightning, you might have a spike in the input voltage, which could damage our devices that's plugged into the wall. So we would want to isolate our devices, meaning our load, from any change in the input voltage, right? And that's where the Zener diode comes into the picture. The Zener diode has a property of holding the voltage across its terminals constant. So if you plug the Zener diode in parallel with a load resistor, the voltage across that load resistor RL would remain constant at VZ. VZ would be the Zener diode voltage. So VZ, and if we were to state VL as voltage across the load resistor, would be the same quantity. VL is equal to VZ, right? So we have current IS coming from the supply, and that is split in two. One portion goes down here through the Zener diode, the other one goes to the load resistor. So let's say V in changes, okay? Let's say V in changes, which is the supply voltage right here. If that supply voltage changes, what happens to the output voltage? That should also change, right? So if V in increases, our output voltage would also increase. Now, if you have a Zener diode in there, Zener diode holds the voltage constant. So what happens to all of that extra voltage? Series resistor, yes, but also when the voltage increases, what else increases with it? The current increases. So if voltage increases, current IS also increases. It goes up. So you have more current coming through here. That total supply current is split in two. It goes through the Zener diode, and the other portion goes through the load resistor. If you apply KCL at the top, the supply current IS is split between IZ and IL. So far, so good? Yes. Yes, I'll get to that. We'll get in the analysis in just a little bit, but first want to finish with the explanation. We are almost there. So IS is split into IZ and IL. As IS increases, IZ and IL also would increase. However, the Zener diode voltage is held constant. That means VL is not changing. So if VL is not changing, then IL should not also change. The only other quantity that can change is IZ. Okay. Supply voltage increases, current increases. If current increases, one of these two should increase. But since the voltage is held constant, the currents should increase. If the voltage is constant across a resistor, then the current will also be constant. It's a linear device. So if VL is held constant, then IL is also constant. The only other current that can increase is IZ, which from the property of a Zener diode in reverse bias, IZ can increase by a large amount. And that's how voltage regulation would work. If the supply voltage increases, then Zener diode will sink more current through itself, thus keeping IL constant. And if IL remains constant, then VL remains constant. Hence, it works as a voltage regulator. So let's sit on this explanation for a bit before we get into the equations and calculation. Let me know if you have any questions. Any questions? Depends on the power rating. So question being asked is how much can IZ withstand? I mean, how much IZ can the Zener diode sink? That depends on the power rating. So it depends on the geometry and the fabrication process. We can make it large geometrical designs with heavy doping. Yes. Not yet. It'll be in the next slide. Does the explanation make sense on how it works? Right. So let's look into the analysis then. So IS is equal to IZ plus IL. Right? Total source current must be divided between Zener diode and between RL. The series resistor is in series with the power supply. Hence, the total current that's coming through there must pass through the series resistor R. So we simply plug the values in. Source current IS can be determined by applying Ohm's law to this 5 kilo ohm resistor. And then IL is simply VL over RL. IS is VS minus VL. VS is here and VL is here across the two nodes of the resistor. So VS minus VL over R. Plug in all the known values. We are given the supply voltage, we are given the Zener voltage, we are given the resistor values. Plug all of those values in. The only unknown is IZ. We solve for IZ. And IZ is 2 milliamps. It's 2 milliamps, positive number. That means that the diode is on and our assumption would be valid. Okay. Unlike the diode models where we analyze a circuit by assuming diode is on or off, Zener diode models right here, it doesn't make sense to use it as off. If it's off, then there's no analysis to be done. It's simply an open circuit. Okay. So coming back to that point, the question that was being asked earlier, right? And the point is that the supply voltage must be greater than VZ, the Zener voltage, in order for the diode to turn on. In this case, VZ is 5 volts and supply voltage is 20. So our assumption would be that the diode is on, right? Yes. Yes. So that resistor is accounted here. And that's where the design, so the question being asked is, if we have a series resistor here, how would that affect the circuit, right? I mean, would it not cause the diode to not turn on? And that's a very good question. So as part of design of a regulator circuit, there are minimum and maximum values for both the series resistor and for RL. Okay. There are minimum and maximum limits for the values of both resistors. If you have a large series resistor value, then it's going to drop a large portion of the supply voltage across itself. Zener diode doesn't turn on. So there's a maximum limit on the R value. And there's also a minimum limit, because if there is a very small resistor, then the current goes very high. If the current goes very high, IS, if it goes very high, then IZ would increase disproportionately. And if IZ exceeds the current limit for the Zener diode, your diode's going to blow up. Again, there are minimum and maximum limits for both series resistor and for RL. If the series resistor is low, if this resistor right here is low in value, then IS would be large. If IS is large, IZ would be high, or IZ would be large. If IZ is large, it might exceed the power rating of the Zener diode. The diode would blow out. So there is a minimum and maximum limit. Okay. If it's large, if it hits it, if it goes beyond its max limit, then it's going to drop a large portion of the supply voltage here, and VZ might not be, it wouldn't exceed VZ as 5 volts, so it wouldn't turn on. And that's shown right here. For proper regulation, meaning Zener diode turns on, it sinks current through itself, and it keeps IL constant. IZ must be greater than 0. It must be conducting, right? Zener diode needs to turn on. If it turns on, Zener diode will conduct some current, meaning IZ would be greater than 0. So you take the equation from above, which is right here, and you say that must be greater than 0. You take IL on the other side, and you get this relationship, where this current, which is IS, must be greater than IL. And so VS minus VL over R refers to this current IS, and VL over RL refers to the current to IL. Yes. Well, current regulator would mean this current through here is held constant, which is also part of the regulation. Yes, because we can have, it's a linear relationship, right, between voltage and current. If the voltage is held constant, current is also constant. Where? Here? Oh, here. So constant current coming through. Yeah. Okay. What was I? Oh, I was here. So the total supply current must be greater than the load current. If the supply current is greater than load current, that means Zener diode is sinking some current through it, right? The remaining portion, and then it turns on. And so for that, RL also has a minimum value. So we rearrange the terms and we obtain that RL must be greater than this component right here. So there's a minimum value of RL. If RL goes below a minimum value, then again, Zener diode will not work. So there is limits for both series resistor and for the load resistor. All right, let's take a pause. Questions? Any questions? All good? Okay, so here, look at the value. I mean, we have a extra RL in there, but the current for the Zener diode is now 2 amps. I mean, 2 milliamps. Previously, by itself, not here, sorry. This one is series resistor, 20 volts, 5 kilo ohms, 2.9. But when you add a load resistor, it's sinking some of the current, and IC is now 2 milliamps. Okay, so same Zener diode, but how RL values would affect the current flowing through the Zener diode. Okay, currents dropped. So if the current to the Zener diode drops below a certain level, then it's not going to turn on. So both RS and RL affect the operation of the Zener diode. Then let's put the series resistor into count. So using the piecewise linear model, Zener regulator using VZ and RZ. Okay, the analysis remains the same. That doesn't change. The only thing now is that there is a slight voltage drop across that Zener resistance of 100 ohms. And because there is a slight voltage drop here, the voltage appearing across VL is not exactly the same as VZ. Okay. So VZ is rated at 5 volts. RZ is 100 ohms. And of course, that's in series. So you perform the same analysis. IS is split between IZ and IL. You plug in the equations for all three. Yes.
Going back to the there's not enough current at the cathode of the unit diode, it won't work.
Mm-hmm.
But couldn't it even still work if your if you get a put 0 amps as long as that other chip as long as the terminal there is great, it's 5 volts, 5 volts off.
Here.
Because I remember there's the problem on the homework. There's what is the minimum value of RL, and you just use the current going to the unit.
That was for the ideal case. So if let's say if the voltage here was 4.9, then everything is going through here. Nothing is going to the Zener diode. That's what it would be.
Yeah.
for the Zener, current dependent. In a way, but we'll mostly use voltage as for the initial analysis. Yeah. Okay. All right. So then from this point on, we plug in all the known values. Once you plug in all the known values, the only unknown left is VL. VL, of course, is the voltage, and sum VL is VZ plus VRZ. Voltage drop across the Zener diode and the Zener resistance. And so we obtain VL as 5.19 volts. Okay, 5.19 volts. If VL is 5.19 volts, we can now find IZ. IZ can be determined by finding the voltage across RZ. Find IZ as 1.923 milliamps, which is greater than 0. Hence, our diode is on. Yes. So VL would be here, and VZ is here. So the question being asked is, how do we find the current across here? And so that would be VZ, hence VL minus VZ. So again, for voltage regulation and for line regulation, minimum and maximum limits for R min for the series resistor and for the load resistor. Okay. How well can the Zener diode work as a regulator? Right. So we just spoke about how the supply voltage can change and how the load resistor could also change. Well, how well the Zener diode can function as a regulator in response to a change in the load resistor RL is defined as load regulation. Load regulation. Okay. In the lab, we can do VL or RL, or change in VL as a response to change in RL, right? RL could change, meaning the load resistor values could change, but your VL must be held constant, right? So change in VL should be 0. Okay. If RL changes, that changes the load current, IL. Hence, the change is monitored as dV or DI, or dVL or DIL. Changes in RL would create changes in IL, load current. So load regulation is a measure of how well the Zener diode is functioning for different load values. Okay. And then there's line regulation. Line regulation is basically how well the Zener diode can function as a regulator in response to changes in the input line voltage. Okay, the input line voltage. So it's dVL over dVs, or supply voltage. Yes. Yes. Because RL could change, small amount or large amount, doesn't matter how much it changes, that would be a corresponding change in IL. But VL, ideally VL would be 0. I mean DVL, sorry, not VL. DVL, change in the load voltage. If the Zener diode is functioning as well as it should, or if it's functioning as an ideal Zener diode, then VL shouldn't change at all. If RL changes, if your RL was 1 kilo ohm, now you change it to 2 kilo ohms, Your resistance is now twice as much, so your current is half. If your current reduces, how much does your load voltage change? Your load voltage shouldn't change. Your load voltage should remain the same. If RL is 2 kilo ohms, your voltage VL should still be 5 volts. If RL is 5 kilo ohms, I mean, depending on the design of the circuit, then your VL should still remain 5 volts. So change in VL, 5 minus 5, 0, should remain at 0 for ideal Zener diodes, not for, yes. So there's a small derivation that's in the book. So I would say keep up with the assigned reading. And those reading dates are more like reminders, right? So there's not actual due dates on there. There's no penalty on it. It's extra credit reading. As long as students finish those readings, you just get the extra credit points. So as soon as the topic is covered in class, or even before it's covered in class, it will be the student's responsibility to just keep up with the reading. But there's a small section and a paragraph in the book that you can look up. Let's see. Oh, this was an example of a power supply circuit. So we have a bridge rectifier network, current limiting resistor, capacitor, filter capacitor. So this would be what we studied so far, right? And the output at every point would look like this. That's drawn in blue. So here, the output will look like a sine wave. Output here would look like a rectified waveform. Output here would be with some ripple. And then output here should be like a flat line. This flat line would be due to VZ. Yes. Yes. Not ripple voltage, just this entire, well, we would choose a value that is higher than VZ. You would work backwards. So the question being asked is, how would this function? So let's say we want, let's stick with 5 volts, right? So let's say VZ is, RL requires 5 volts. Then we choose a Zener diode of 5 volts. Okay, VZ would be 5 volts. So then we would work backwards. If Zener diode VZ is 5 volts, then this value right here, the output of the filter capacitor must be larger than 5 volts. So the peak-to-peak ripple, the DC component should be larger than 5 volts. So the peak-to-peak ripple is above 5. To be safe, we choose something like 6 or 7, or even larger than that, like 7, 8, 9, 10 volts. Okay, so this point right here would be close to 5, not 5, sorry. 6 would be cutting it too close. It would be 6 to 8 volts or larger. Okay. And then before the capacitor, of course, this peak value would be, can be anything, maybe like 12 volts or larger. Okay. And this here should be about 25 volts peak to peak, the output of the transformer. Probably even bigger than that. Yes. So line regulation is regulation fluctuations in the line voltage. Load regulation is fluctuations in the load resistor. Supply voltage changes, the output should be regulated and stay constant. So line is basically think of it as the power line, the voltage coming from your power supply. That's line regulation. Now, if your load changes value, that's load regulation. In yes, load voltage is the cathode. So line regulation is fluctuations in the input voltage. Load regulation is a fluctuations in the load resistor. In general, physically speaking, resistances and devices get hot, right? What happens to resistors, regular resistors, when it gets hot? Regular resistors, right? PTC and NTC, positive temperature coefficient, negative temperature coefficient. Some devices would go up, some devices would go down. Low resistors would go up. So if it's just a pure resistor, resistance would increase. But RL in this case, we are just using a simple resistance, but RL could be any device. Could be your smartphone, could be your tablet. Everything will have some sort of impedance and resistance, right? So once you are using it, it's going to change in value. So the load will always change in value. It'd be minor changes, still will be changed. Okay. All right, 15 minutes left. Let's go to two last circuits, clippers and clampers. This is what we're doing in the lab this week. Diode clippers and diode clampers. Clipper, and we're going to use ideal diode models to quickly analyze these, right? Quickly as in perform a quick analysis. Clippers are so called because they're used to clip the waveform, the AC waveform. Okay, so here's a single diode, and you have some sort of sinusoidal input being applied to the diode through a resistor R. V in on the left, V out on the right. Okay, positive half cycle. In the positive half cycle, the diode is on because anode is towards the positive end. So if it's replaced with a short circuit, V out is equal to 0. You're taking V out across a short circuit. So V out is equal to 0. Negative half cycle, diode is open. V out is equal to the supply voltage V in. So the resulting effect, or the cumulative effect of the diode in one cycle, is that we have output equal to the input in the negative half cycle, and we have 0 output in the positive half cycle. So the cumulative effect is that the positive half cycle is chopped off or is clipped off. Again, ideal diode model, positive half cycle, diode's on. If it's on, V in does not reach the output. V out is equal to 0. Positive half cycle, 0 volts. Negative half cycle, diode is off. Whatever you apply at the input reaches the output. And so the cumulative effect is that the positive half cycle is clipped, hence a diode clipper. Make sense? If you reverse the direction of this diode right here, what happens? Yeah, V out will be equal to V in the positive half cycle, but it'll be clipped in the negative. So negative half cycle is chopped off. So it would be, it'll be the opposite. It'd be off here. Sorry, it'll be off here and on here. So negative half cycle will be clipped. So you have positive clipper shown here, and negative clipper would be when you reverse the diode. Okay. Other clipper circuits, you can put the diode in series with the power supply. You'd again use the ideal diode model. Positive half cycle, diode is on, so it provides V out. Negative half cycle, diode is off, no V out. Okay, so this would be a negative clipper. Yes, you had a question? Okay. I thought, okay. All right. 150. What if we attach a battery in level? Yes. Yeah. Yeah. So we are not performing any mathematical analysis for this. Yeah. But it'll be the same as the previous circuits. Apply KVL, apply KCL, you can figure out what the voltage drop is across the resistor, and you can figure out what V out and V in is. Again, this is ideal diode model, but if it's constant voltage drop or real diode, 0.6, 0.7 volts would drop across the diode itself. So the entire half cycle would not be clipped. In the positive half cycle, you would expect like 0.7 volts, and you will see that in the lab today. Well, at least those of you are taking the lab today. If you attach a voltage source in there, what happens? So in the circuit on the right, the anode of the diode is held at plus 4 volts. Okay, anode of the diode is held at plus 4 volts, which is right here. You see that? Okay, that point. Now, we are still using the ideal diode model, right? So if the cathode is at plus 4 volts, sorry, if the anode is at plus 4 volts, that means the diode does not conduct until the cathode is right there on the screen, right there, right? So the cathode is less than 4 volts, diode is on. If the cathode is greater than 4 volts, diode goes off. When will the cathode go higher than 4 volts? In the positive half cycle. So if we apply a sine wave, and let's say this is a random value, let's say cut it off at 4, so let's say 10 volts. Okay, so let's say V in was 10 volts, and this is minus 10 volts. Okay, so in the positive half cycle, the diode does not turn off until the cathode goes higher than 4 volts. Okay, so before that it's on, and because it's on, what happens? It behaves like a short circuit, and your V out is simply the voltage of that battery, plus 4 volts. Okay, so below 4 volts, your V out is a constant flat line coming from the battery, so which is indicated right here. Your input crosses 4 volts, diode turns off. When the diode turns off, V out is equal to V in. And so you obtain V out equal to V in for that portion of the sine wave. Then sine wave goes to 10 volts, starts dropping 10, 9, 8, 7, 6, 5, 4. And as soon as it drops below 4 volts, diode turns on again. Diode turns on, your battery is now connected to the output. And so again, it's a flat line. Make sense? And in the negative half cycle, diode's going to be always on. Cathode's always less than the anode, so it's always on. And because it's always on, in the negative half cycle, you obtain a flat line of 4 volts. And that's it. That's how you would analyze this circuit. So in the positive half cycle, it looks like this. Negative half cycle looks like this. Okay. Using the ideal diode model, you should be able to analyze a circuit if the diode polarity was reversed, if the battery polarity was reversed, or if the diode was connected in series right here. Okay. Doesn't matter what kind of circuit is, but the steps that you use would be exactly the same as we did here. Make sense to everyone? You always take a look at the input, see what is required to turn the diode on or off. How does the diode behave in the positive half cycle? How does it behave in the negative half cycle? Redraw the circuit with the model like this and like this, and then check what is V out. Okay. That's how you can analyze any diode circuit. And then last, we have a clamper circuit, diode clampers. Diode clampers are very useful circuits to clamp the AC signal at a particular DC level, meaning we use it to apply a DC component to our AC signals. So oftentimes it happens, especially when we use amplifier circuits, your amplifier circuit will insert a DC component to your AC signal, either positive or negative. And so we would want to remove, in this case, we want to remove it, but in some other cases, we might want to add it in. So in either cases, we'd want to either add or remove a DC component from our output signal. So a diode clamper uses a capacitor. Right? It uses the energy storage capacity or energy storage capability of a capacitor. You have a diode connected across a load resistor in parallel, and you have a capacitor in series. Let's say we apply a square wave input. This can work with any AC signal, but let's say we apply a square wave input, right? What happens in the positive half cycle? Positive half cycle, diode behaves like a short circuit. If it behaves like a short circuit, then V out should be equal to 0 volts. In the negative half cycle, diode is off. If diode is off, then V out is basically capacitor and V in. Okay, VC plus V in, because it's in series. In the positive half cycle, because the diode is in series with the capacitor and parallel with the output goes to 0. However, the capacitor has a pathway to charge. Yes. So V in over 2, because it's only half the cycle. Half the input. It could be, no. So V in, I'm just saying V in is 2 times VP. This is VP. This is minus VP. It's just V in is basically peak to peak value. That's all it is.
If it was to be in, we're referring to being amplitude.
Just amplitude, yeah. That's all it is. If it was 10 volts peak to peak signal, it would just be 5 volts. We could just say fine sine omega t, 5 cos omega t. It would still mean the same thing. It wouldn't be V in over 2. V in over 2 just refers to this circuit. Doesn't refer to anything else. It's simply volts peak to peak. Anyway, in the positive half cycle, diode is a short, and because it's a short circuit, capacitor charges in this direction, right? It's going positive. So you have plus on the left, minus on the right. Negative half cycle, diode is off. V out is now connected this to this point right there. And between those 2 points, what do we have? We have a capacitor that is now in series with your supply voltage. So capacitor in series with your supply voltage, meaning we have twice the value of the input. And so your voltage is now clamped at V in. Voltage is clamped at V in, yes. No, the output, sorry. Not capacitor voltage, output. Output is VC plus your supply voltage.
In the negative half cycle, is VC still equal to Vn over 2?
In the negative half cycle, capacitor tries to discharge through the resistor, but if the resistor is large enough, if this resistor R is large enough, then the capacitor cannot discharge appreciably. It would simply appear as a DC voltage source in series with your AC voltage. And so it gets clamped, it gets added on, and you have V out is equal to VC plus your input voltage. Yes. VC could be any value. Let's use numbers. Let's say your V in is 10 volts. This is volts peak to peak. So VP is 5 volts. So your VC would be 5 volts. In the negative half cycle, V out would be VC plus V in over 2, which would be 5 plus 5, 10 volts. I think the V in over 2, upon reflection, seems like a poor choice for explanation. It's simply peak to peak voltage. Whatever input voltage we're applying, half of that input voltage, if it's in the positive half cycle, then it's going to go appear across the capacitor, and then the other half appears in series. Yes, yes, and yes. Go. Yes, when it's a short, capacitor is charging. No. So when it's open, the time constant of the circuit, if this is R right here, time constant tau is R times C. When it's charging, it's RD, the diode resistor. RD would be far smaller than R. So it charges at a faster rate than it can discharge. Okay, so it's a good question. It's charging at a faster rate than when it is discharging. It's discharging at a very slow rate. So the discharge capacity, so diode resistance might be what? Tens of ohms, 100 ohms. Your R discharge would be in thousands of ohms. So 1,000, orders of magnitude or charging versus discharging. So yes, there will be some discharge, but it'll be so small as to be negligible because the frequency of operation would be far higher, right? You would be applying a signal maybe hundreds of hertz, maybe in kilohertz. So signal frequency is far higher than the capacitor doesn't have enough time to discharge. So it charges very quickly, discharges very slowly, and then the entire thing appears across the output. If you were to slow down your rate, I think we have gone way over time. So if you have to leave, it's fine. But if you slow down, let's say you apply a 1 hertz signal or even smaller signal, 0.5 hertz, you might be able to see a small discharge slope. So you can try that in the lab. Okay. And there were 2 more questions, right? So we'll end class here today, but I can still answer those questions.